Maneuvering during slow flight. Now, this is a maneuver on both the private pilot check ride as well as the commercial pilot check ride. And this is going to be an extremely important maneuver. And it's when we operate the aircraft when the airspeed is just above stall speed. There's little margin for error, and this maneuver will greatly improve your piloting skills, including your approaches to landing, and it'll definitely help your landings, especially when you're in that flare and operating that aircraft above the runway during the flare stage of landing. So, what is slow flight? It's when we're flying at a slow speed at which any increase in angle of attack will increase or will result in a stall warning. So our aircraft performs and controls differently at lower speeds when compared to higher airspeeds. So maneuvering during these low flight speeds, the flight characteristics and degree of controllability of the aircraft near the critical angle of attack is different than when compared to higher speeds in normal operations. And we'll enter these regimes of flight whenever we're doing things like taking off, landing, doing a go around. So learning how the aircraft performs and is controlled at reduced speeds is essential. All right, so slow flight, what is it? Technically, any speed less than cruise, but within this training context, like I said, it's when we're flying at a high angle of attack in which any further increase of our angle of attack or load factor will result in a stall warning. Now, the objective is to understand slow flight characteristics and how the plane performs near the critical angle of attack. So, airspeed. Increased airspeed means an increase in lift. So, if I increase my airspeed, I'm increasing my lift and I can lower my angle of attack to maintain my altitude. If I decrease my airspeed, then I need to increase my angle of attack by applying back pressure on the yoke to raise my angle of attack in order to maintain altitude. So in relation to slow flight, the slower the airspeed we go, the higher the angle of attack we're flying. All right, now let's talk about the region of reverse command. Now, this is one of the most important aspects to understand when we talk about slow flight. So let's say, normally we operate in the region of normal command. And the way we differentiate between the two is this is our total drag graph, right? It's the sum of our parasite drag, this red line, and our induced drag, this yellow line here. The sum of both is our total drag. If I split this down the middle from where my lift drag max is, this side will be the region of normal command, this right side here, and this left side will be the region of reverse command. So in the region of normal command, as airspeed decreases, say I'm cruising at this speed right here, as airspeed decreases, and remember this y-axis is my total drag, as airspeed decreases, drag decreases until hitting our lift drag max. So if I want to go faster and say I'm at this speed but I want to travel this fast, I run into additional drag, which requires additional thrust to create that, to maintain that airspeed. Basically, if I was flying at cruise and I told you, hey, I want you to increase our airspeed, well, then you would add power in and then our airspeed would go up, and because we added that additional thrust, now we're cruising up here. If I told you to make a climb, you would move your pitch. So I wonder if I can make a notepad for this. So for the region of normal command, I use my pitch for my altitude. So again, if I was in cruise and I told you to climb, you'd pull back on the yoke. And if I told you to go faster, then I would add power. So power equals airspeed. Now let's add the reverse command. One of the tricky parts of the region of reverse command is that this is swapped. So I'm going to use my pitch for my airspeed. I'm going to use my power to control my altitude. So that's why it's called region of reverse command, because it's backwards. We pitch for our airspeed, power for altitude. So in this region of reverse command, if I slow down, I run into more drag. And if I speed up, I will run into less drag. And so it's the complete opposite of the region of normal command. So if let's say this is my like total drag curve, right? This is this orange line right here. I'm just kind of drawing it quickly. And this is my, my best glide airspeed, right? Our lift drag max. This is the region of normal command in here, on the right here. And this is the region of reverse command. Now if I'm flying in slow flight and I'm at this point right here, and remember the y-axis here is drag, and then the x-axis here is, it's hard to draw with my mouse, airspeed. Alright, so if I'm at this point right here, and I get even slower, now I run into even more drag, causing my airspeed to slip unless I make a correction. So I have the tendency to continue to go this direction. If the aircraft starts to speed up, I run into less drag, right? The drag at this line compared to down here. So the airspeed in the region of reverse command has the tendency to slip away from you. So it requires additional pilot control forces and being on top of your pitch and your power in order to maintain a set airspeed. When compared to the region of normal command, and I'm flying at cruise at this airspeed, if I start to speed up, I'm going to run into additional drag that'll situate me back at my airspeed. So the tendency to remain stable at this airspeed is inherent in the region of normal command. So our airspeed in reverse command will slip away. Normal command, again, if I slow down, I'm going to run into less drag, speeding me back up, allowing for that airspeed to be stable, unlike the region of reverse command. And so when we operate in this region of reverse command, when we are operating in slow flight, I'm pitching for my airspeed, and I'm using power to control my altitude. All right, slow flight aerodynamics, we're talking about some yaw effects. So these are our left turning tendencies. When we operate in slow flight, we're operating at a higher power setting, which means we'll be running into more torque reaction. And we're also operating at a high angle of attack. So our asymmetric loading, or P factor, left turning tendency will be noticeable. So we need additional right rudder. The higher our power setting, the higher our angle of attack, in order to offset these left turning tendencies. We're not going to be feeling gyroscopic action as much unless we're initiating a descent or spiraling slipstream, because we're not traveling through as much air. So less air is going to be hitting our vertical stabilizer. So anticipate in considerable right rudder to maintain coordination when we're in slow flight. We're almost like stepping on the right rudder really hard throughout the entire maneuver. So big picture, right turn requires even more right rudder because we're working again left turning tendencies and adverse yaw when we're in a right turn. In a left turn, our adverse yaw will kind of counter some of those left turning tendencies. So it'll require less right rudder. So when we're maneuvering in slow flight, let's talk about maneuvering loads and turns. Remember, our load factor is the ratio between the amount of lift we're creating to the weight of the aircraft, and that's measured in G's, or G-forces. Increased load factor has a correlation with increasing stall speed. So think about how when we're in slow flight, we're already operating very close to our critical angle of attack. Now, if I enter a bank that's associated with increasing load factor, which increases stall speed, and I'm already operating close to my stall speed, that means turns in slow flight, we have to be cautious about how we do it. So when we do turns in slow flight, Increased load factors associated with level turns in slow flight can quickly result in a stall, which is why we use gentle control forces and low bank turns. So we'll only stay at about a standard rate turn, and of course staying coordinated while we're in slow flight. We don't want to be banking the aircraft more than about 5-10 degrees, really about 5 degrees, because any more bank that we add, we're increasing load factor, which exponentially increases stall speed, and we're already operating at a low airspeed, and that can result in a stall. Weight when it comes to slow flight. Heavier aircraft require a higher angle of attack to maintain level flight. That means it's operating closer to the critical angle of attack when compared to a lighter aircraft. A heavier aircraft is more stable. In the case of a stall, that heavier aircraft will have a larger tendency to go nose down after in the stall, to regain airflow back over the wings. Increased weight and stability can assist in controlling the aircraft. All right, and we'll talk about center of gravity. So I went into depth on this pretty really in depth on my performance and limitations video. I'm going to kind of quickly go through it here. A forward-loaded aircraft acts heavier. It's got a heavy nose because of that more forward center of gravity. There's a stronger tail down force, meaning we have to create more lift. We do that by flying at a higher angle of attack. By flying at a higher angle of attack, we have more induced drag, and we have a higher stall speed because we're flying at that higher angle of attack. We're that much closer to that critical angle of attack. And stall recovery becomes easier because we've got more weight further forward to give that aircraft the tendency to nose down in the case of a stall. An aft-loaded CG acts lighter and is faster because we're flying at a lower angle of attack. We don't have as much tail down force, so we don't need to create that additional lift when compared to the forward-loaded aircraft. So we're flying at a lower angle of attack, meaning less induced drag, meaning faster cruise speeds. And since we're flying at a lower angle of attack, we are farther away from that critical angle of attack, giving us a lower stall speed. And stall speed recovery is more difficult than an aircraft with a forward-loaded CG. There's just less of a tendency of that aircraft to nose down. Now, an aft CG isn't, better or worse because the stall recovery is more difficult. If we're still operating within the envelope given to us by the POH that the manufacturer sets, it's still going to be operating safely. But yeah, in fact, most airliners are operating on the aft side of their CG due to the fact that with an aft CG they fly faster, and flying faster, the airline saves money, and it's still completely safe. It's just, I've heard people talking about how an aft-loaded CG is bad and a forward-loaded CG is good. It's not good or bad, but we just have to understand the differences between the two. Okay, slow flight and critical flight situations. So where we operate in slow flight, or where we're operating in this regime of the region of reverse command, is during things like takeoffs, climbs, landings, and go-arounds. All this, we're on the backside of the power curve, and this is just another way of saying we're in the region of reverse command. So again, we're in the region of reverse command. We're operating beneath our VG airspeed, and we have this tendency here of our airspeed to slip away, causing us to require more pilot forces, or what's the best way to say that? To be more adamant on maintaining our airspeed and altitude. Inadvertent slow flight, if we accidentally get ourselves in slow flight. So we have to maintain proper control and recovery, and a lack of understanding of slow flight could lead to loss of control. So again, precise control is critical when close to the ground and in the region of reverse command. So we'll talk about slow flight, sight, sounds, and feel. It's going to be a lot different than when we're flying at a higher airspeed in cruise flight. The sight, we're going to be in a nose-high pitch attitude. We're going to be seeing more sky than normal. So a lot of visual references that we can use right in front of us aren't going to be as available. So if you live next to somewhere that has a giant mountain that you can still use, because you still get that side picture great. If you're in the Midwest and it's all flat, then you're gonna run out of sight pictures because it's just the horizon and farmland everywhere, and it's really boring out there. Sound. Decreased sound is there's less airspeed flowing around the aircraft. We might even hear the stall warning horn. So just be aware of that. If we hear that horn, knowing what that is, and if our airspeed's getting too low and we're about to stall, making that change, lowering that nose, adding some power, and changes in engine noises. We're operating at a higher power setting, so we're going to hear the engine working a little bit harder than when we're at normal cruise flight. Oh, that's not necessarily true if I'm adding flaps and maybe I'm at about 1900 RPM compared to maybe the 2300 RPM. So scratch what I just said there, but the change in power setting will be different than what it'll be in cruise flight. And feel. Controls will become mushy and less responsive. That's because there's less airflow, traveling around our flight controls, and so the same, if I turn my yoke to the left maybe like 2 or 3 inches at high speeds compared to low speeds, it'll be completely different. Like moving your if you're driving on the highway and you turn it, turn the wheel 90 degrees versus turning the wheel 90 degrees when you're going through a parking lot. That's basically why the controls will feel mushy at these lower air speeds. Additional right rudder is required because we're flying at low air speeds. And in order to create enough lift to maintain our altitude, we increase our angle of attack. When we increase our angle of attack, we increase P factor, or asymmetric loading, which leads to that left turning tendency. So we counter that with, again, our right rudder. And we might feel a buffet. So as airflow travels over the wing and airflow becomes separated, there's less tail down force pushing down, which will kind of feel like the aircraft is shaking. And sometimes you'll feel the buffet, sometimes you won't. And so with that is just less tail down force, and leads to that buffet shaking feel inside the aircraft. Stall warning, range, and limitations. So we talked about the buffet. Tends to occur prior to the stall horn. Stall horn may not always occur. The stall horn, designed to give a warning of approaching stall, so it's usually set just lower than the critical angle of attack when the stall will make a noise to warn you of an impending stall. All right, performing slow flight. Again, we're going to pitch for our airspeed once we're in that region of reverse command and use our power for altitude. We're going to be using considerable right rudder to counter for those left turning tendencies and potentially overbanking tendency in turns. So potentially if we're doing shallow banks, potentially having to do some counter aileron, some opposite aileron in the turns. And this is the hard part right here, right? 90% of our eye vision needs to be outside, 10% inside. This is the hard part, especially when our airspeed is tending to slip away from us and we're operating in slow flight and we have to maintain our altitude, maintain our airspeed. We're doing a lot of things. We're making a turn while climbing. Still got to keep 90% of our vision outside. Use visual references. If you've got your heading on a certain visual reference point, align that up with a point on your dashboard and keep it there. And just scanning inside. If you see your airspeed's getting low, your airspeed's getting high, make a change, get your eyes back outside. So pre-maneuver, we'll do our pre-maneuver checklist, doing a clearing turn, making a radio call, setting up the airplane, or briefing how we're going to set up the airplane, and then going through talking about the procedure we'll go into in the case of an emergency. We'll pick an altitude no lower than 1,500 feet AGL, and we're going to configure. So when we enter slow flight, we're going to be using flaps. So when we establish, we're going to gently reduce power. Remember, as that airspeed bleeds, we're creating less lift. So in order to maintain our altitude, as we pull power back, we're going to slowly start to bring that nose up as that airspeed starts to go down. And that will allow us to maintain our altitude. As the airspeed falls, we'll lower flaps as the airspeed limits allow us to. So for us, under 110 knots, we can go flaps 10, and then under 85 knots, we can go flaps 2 and flaps 3. Approaching our slow flight speed, which in our 172 is 50 knots. So we'll want to stay within that 50 to 55 knot range for slow flight. We're going to be reintroducing power as I get down to that airspeed, so about 1900 RPM or so, and then make small, 100 RPM changes depending on what's needed. Just enough to maintain altitude and airspeed. And this is where we start to do our pitch for airspeed and power for altitude. So if we start to get fast, pitch up and you'll start to slow down. And we're making small control changes, so changing my pitch 1 to 2 degrees at a time. And generally, we'll sometimes need parallel power changes. So if I'm, excuse me, if I am potentially fast and I'm high, I'll need to pull that power out and then get that nose back down, but not so fast as to increase my airspeed too much. And then we'll use our power for our altitude. So if I'm low, I'm going to increase power, and if I'm high, I'm going to take power out, and generally requires a parallel power change. So if I'm low and I add power, my airspeed might start to go up, so I'll add power and raise the nose. Or if I'm high, I'll take power out and I'll lower the nose. So I'm constantly changing my pitch for my airspeed, changing my power for my altitude in order to maintain that airspeed and that altitude. I want to maintain my heading as well using a visual reference, and in level turns I'm going to do smooth, gentle banks, maintaining coordination and adjusting pitch and power for airspeed. And generally in turns I need to add additional power in order to maintain altitude. Climbs and descents, so if I'm climbing, I'll add full power and then adjust my pitch to maintain that 50 to 55 knots. If I'm descending, maybe I'll bring that power back to about 1500 RPM and pitching down to maintain that airspeed. Returning to cruise flight, so after we complete the maneuver, smoothly apply full power and right rudder, lower the nose, start to clean up our flaps. As we approach cruise speed, we'll reduce the power back to our cruise setting and then trim for cruise flight, and then go through our cruise checklist once again. So some common errors for slow flight are not clearing the area, inadequate back pressure as power is reduced. Remember, as our airspeed goes down, we need to create additional lift by increasing our angle of attack. So that's why we need to be adding that back pressure as we're entering slow flight. Excessive back pressure as power is reduced, resulting in a climb. Insufficient right rudder to compensate for the left yaw, for the left turning tendencies from our P factor. Fixation on instruments, we're flying visually, keeping our eyes outside. Failure to anticipate changes in angle of attack as flaps are extended or retracted. Remember, as we add flaps, that nose is going to want to balloon. So we'll add the flap and then keep that nose down where it needs to be. Inadequate power management. If I'm starting to get low and I try to correct by taking power out and I get even lower, that's going to be a problem. Pitch for airspeed, power for altitude. Add power when I need altitude. Increase pitch when I need to decrease airspeed, and vice versa for both of those. Inability to properly trim the airplane. The trim is supposed to help us, so this will help us maintain our airspeed. If I trim for 50 to 55 knots and then I'm using my power to hold my altitude, that makes the maneuver a whole lot easier. And failure to respond to a stall warning. Usually if I hear the stall warning, I'm getting too slow and I'll need to add power and or decrease my pitch. So some hazards is turbulence, which can increase stall speed because you can have sudden loads that can cause you to exceed the critical angle of attack. Below LD max, the aircraft exhibits speed instability like we talked about, so the speed will tend to slip away, which is why we need to be on top of making these pitch and power changes as our airspeed starts to trend away from where we want it to be. Microbursts, wind up to 100 knots and downdrafts up to 6,000 feet per minute. If we enter a microburst, then we want to climb immediately, VY climb. And we're not going to be flying in around thunderstorms. Higher density altitude means less performance, so less power, thrust, and lift. I'm going to kind of speed through this, staying away from collisions and keeping a proper scan, 90% of eyes outside, 10% inside. We're going to be careful of the terrain. We don't want to be a CFIT, case study. So we're going to be choosing safe altitudes and safe practice locations and staying well above these minimum safe altitudes. Checking our NOTAMs for obstacle wire strikes. Not staying distracted. We're operating in slow flight, and when we're operating in slow flight, we're gonna be focused on that, not on our electronic flight bag or messing around on the G1000. Aviate, navigate, communicate. If we get disoriented, find a way to catch back up to the airplane. And task prioritization, so dividing attention between the aircraft, scanning, and communicating. Remember, it's our job to continue to scan while doing the maneuver. We're still flying VFR. Safety first, aviate, navigate, communicate. And that's it for this one on slow flight.